This lesson's going to sort of seem like an English lesson because we're going to be talking about statements and sentences and different forms of different statements. But we're really getting into our logic and reasoning and building our vocabulary for a big part of geometry, which is called proofs. So we're trying to eventually, we're going to be able to try to prove why triangles are congruent, why things the way they are, and in order to do that, we need to have a solid foundation of reasoning skills. So, this first lesson is called conditional statements. A conditional statement is a logical statement that has two parts. It has a hypothesis, P, and a conclusion, Q. So most statements can be written as conditionals in the if-then form. If, the if part represents the hypothesis, the then part represents the conclusion. So I'm going to rewrite all 30-degree angles are acute, where the all 30-degree angles is the hypothesis, and then our conclusion is that they are then acute in the conditional form with if then. So if an angle measure is 30 degrees, then it is an acute angle. So this is a conditional statement. It is a true statement. An angle that is 30 degrees is acute. How it is written at the bottom of the page is the if-then form. If the hypothesis, then the conclusion. Another key term is called negation. It is the opposite of the original statement. And that symbol is that tilde symbol. That means not. So for example, if our statement is the ball is red, the negation of that statement is the ball is not red. So there's ways that we can reverse conditional statements to rewrite them. So a conditional statement is if the hypothesis, then the conclusion. The converse is the flip. If the conclusion occurs, then the hypothesis happens. The inverse is when we can negate both. If not P, then not Q. And the contrapositive is if not Q, then not P. And you're going to see as we go through this example that sometimes it doesn't create a true statement. So our original conditional is true. If an angle is 100 degrees, then it's considered obtuse. So that is true. So let's look at the converse of that statement. The converse is flipped. So if an angle is obtuse, 100 degrees. 100 degrees. So we're flipping the hypothesis and the conclusion. So if an angle is obtuse, then it is 100 degrees. So let's think about that. If an angle is obtuse, we know that an obtuse angle is is over 90 degrees and less than 180. So if it's obtuse, then does it guarantee that's 100 degrees? That is false. An obtuse angle could be 103 degrees, 104 degrees, 150 degrees. So that created a false statement. Okay, so then the inverse is the opposite of the conditional statement. So if not P, then not Q. So if an angle is not 100 degrees, then it is not obtuse. Is that true? So if we don't have 100 degrees, then that means it could be 1, or it could be 90, or it could be 120. Does that guarantee that it's not obtuse? No, because you could have a 120 degree angle. If it's a 120 degree angle, then it is obtuse. So that is another false statement. Lastly, if not the conclusion, then not the hypothesis. So if an angle is not obtuse, then it is not 100 degrees. Is that true? So if an angle is not obtuse, so we're looking at an acute or a right or a straight angle, then it is not 100 degrees. That is true. So this is not coincidence. The true false statements are actually always going to match. So if the conditional is true, the contrapositive will also be true. If it's false, the contrapositive will also be false. Same with converse and inverse. Their true false statements will always match as well. The last new definition that we're going to look at is biconditional statements. So when the conditional and the converse are both true, we can write them as an if and only if statement. So that is shown as the hypothesis. If the hypothesis is true, if and only if the conclusion is true, and it has double arrows going in both directions. Now, since we accept definitions to be true, we can always write definitions as biconditional statements. So, for example, the definition of a perpendicular line or a set of perpendicular lines. So, our definition is if two lines intersect to form a right angle, so they intersect, they form a right angle, then we can say that the lines are perpendicular. So the converse is that statement flipped. If two lines are perpendicular, so there's our set of perpendicular lines, then they intersect to form a right angle, which is also true. So both our conditional and our converse are true statements. Therefore, we can write that as a biconditional statement. Two lines intersect to form a right angle if and only if they are perpendicular lines. So let's use that definition to look through a couple of questions. They want to know if the following statements are true. So, is line AC perpendicular to line BD? So by our definition, it is two lines that have to intersect, and they intersect to form a 90-degree angle. Thank you to that box. We do know that this is a 90-degree angle, so that is true. Angle AEB, so we're looking at this angle here. And angle CEB, sorry, AEB is right here. And AE and CEB are a linear pair. So thanks to our 90-degree box, we know that BEC is a 90-degree angle. All right, since these are perpendicular lines, that means that its linear pair is also a 90-degree angle. Its vertical angle is also a 90-degree angle, and the last linear pair is a 90-degree angle. So they form a line because it is 180 degrees. So this is another true statement. Last, we are going to look at opposite rays. So our EA, so ray EA and EB, a pair of opposite rays. This is false because they are not collinear.